It's almost time. How's everyone doing? Hello, everyone.
I just got my book in the mail today. Very excited.
Oh, me too. Look what I got.
I think mine is bluer than yours.
It might be the lighting.
Yeah.
What band was
Mine's
that?
pretty blue. What's the song by Stivu or Shivu, something like that.
It was awesome.
It was recorded in an MRI scanner, in a real-time scan, and then re-recorded. I guess it wasn't recorded in the MRI.
Yeah.
The voice, because it would be pretty loud otherwise. A lot of people are inspired by MRI and create a lot of art. So I'll try to show you some of that. Maybe some of my own art. I got some pretty nice artifacts. All right, I think it's a good time to start, as any. Thank you very much for showing up. I really appreciate it. Definitely those that have their picture on. Hi, folks. Really appreciate that too. Gives such a nice feeling to, as if I'm almost talking to people, which is nice. I'm still on the couch, so nothing has changed there. Who has not gotten their book? Raise your digital hand.
I'm still waiting for mine.
So I ordered this immediately after lecture last time, like last week. Arrived today.
So did
So
I.
it doesn't. So it shouldn't take that long, I think. Hopefully you'll get it. And what I'd like you to do is immediately start reading chapter 1, 2, and 3. Okay. Chapter 2 is definitely extremely useful for the homework, which I also recommend to start working on because they're quite long. Their purpose is really to get you up to, to get you up to a certain level that I would expect from you to know about Fourier transforms, linear systems, and so on and so forth. So we'll be able to talk and do the analysis of how MRI works and how artifacts are being done and image creations. So that is all dependent on your knowledge of Fourier transforms and multidimensional Fourier transforms. So I really recommend you starting the homework as soon as possible, and also reading chapter 1 to 3 in the book. The book actually reads really well. I don't know if you know Dwight. Dwight is an amazing character to know. He's a Japanese Hawaiian, so it's pretty chill and mellow person, very reserved in anything that he says, and also extremely accurate and very deductive. And so the book is kind of, I mean, it's very much Dwight. Like normally an imaging book would have a picture of an image, right? Like, but no, Dwight had picked, something like this. Minimalist, elegant, so this is how the book is also written. So it's really nice to read. Very well explained. So in a very simple and nice way. All right, any questions about last time or anything administrative, non-administrative? Yeah, Yuan, are you asking, or you're raising your hand, or is it just still there from
Oh,
before?
sorry, it was the book thing.
Okay. Does the book have background on Fourier transform? Yes, it does. It does, but look, to some extent, I mean, it does have a background on Fourier transform, but the book is not a comprehensive book in that sense. So if you pretty much what we're going to do today is we're going to finish last lecture, or the topic of, you know, the kind of the 10,000 foot view of MR, and then I'm going to go through the entire material of EE120 and EE123 in maybe 45 minutes. So, you know, this is just normally I wouldn't do it, but I am realistic. The fact that not, you know, I have people come from different background, and we do expect you to know this. And if I'm not able to finish this, maybe we'll continue either tomorrow in discussion or maybe the next lecture. But if I want to spend that many lectures on kind of prerequisite material. So we'll see how it goes. All right. But the homework will also cover a significant portion of that. You'll have to do some proofs and derivation. Hopefully that will give you some practice. All right. Cool, super excited. All right, let's dive in. So last time we talked about imaging, and imaging that MRI's multidimensional imaging is quite similar to kind of like a piano in a certain sense. When we apply a gradient, that means that there is now a distribution of frequencies that the spins emit that changes as a function of space. So if we apply an X gradient and we have spins at these three positions, then the tones being transmitted from those spins will correspond to frequencies that depends on their position, higher frequency over here, lower frequency, and even lower frequency. And it was possible to then you know, pick up the signal and through a Fourier transform actually figure out which harmonics correspond to these frequencies, and hence to recover the position. However, remember that this is only done in one dimension, right? It's kind of like a one-dimensional projection, because when we apply a gradient, that gradient is going to be only along one dimension. It's impossible to create a gradient along two dimensions. Does that make sense? Because if I add another gradient, let's say in Y, it basically just rotates that gradient into a direction which would be, let's say, 45 degrees, as opposed to being either 0 degrees or 90 degrees. So it's always just going to be a linear combination of a line. It's always a line. It's just rotated in space. So what we do is, in order to actually resolve where these spins are, we have to make multiple measurements. So we have to excite, apply a gradient, and then receive the signal. And then another way is we excite again, apply a different gradient, and then acquire a signal, which will give us these two tones. Here, the tone is stronger than this one because it's a combination of two. And then a third direction, for example, would be this. Okay, and that will give us other three tones corresponding to the position projected onto the axis of that gradient. So of course, you need more than three tones in order to resolve a two-dimensional space. But if you only have three spins, that is actually sometimes enough, depending on which directions you actually measured. And so the spectra that we're going to get from each one of those measurements is going to look something like that. And by the theory of, I guess, back projection, you can try to solve which are positions of those spins, you know, that correspond best to generating those tones if we apply the gradients. And what we could do is say, you know what, we can say, oh, if we apply this gradient, then our spins are somewhere along these lines. If we apply this gradient, the spins are somewhere along this line. And then if we apply this gradient, the spins are somewhere along this line. And so if I look at the maximum point, then those would be along the intersection of these. And so hence we can perhaps resolve the spin position. Now, obviously, that's very similar to tomography, very similar to how CT work. And in fact, this is how Lauterberg originally described MRI. And it all comes down to the central section theorem, which says that if you have an image and you compute its two-dimensional Fourier transform, so on the right-hand side is a two-dimensional Fourier transform of the image, we call it K-space, by the way, then making a projection in the image also has the same amount of information of collecting one line in the Fourier transform of that image. So if we project along this direction, if we project along this direction, that would give us a line in the frequency domain along this direction. And so if we make another measurement that's the same as acquiring a line in the frequency domain in the two-dimensional Fourier transform along this direction and another one, and you can kind of start realizing like how many projections you actually need in order to cover the entire space, which is the two-dimensional Fourier transform. And once you get it, it is possible to do an inverse two-dimensional Fourier transform in order to recover the image. And again, there's a lot of details here because we're collecting data on a polar grid as opposed to a Cartesian grid, and what does it mean to take a Fourier transform from a polar onto a Cartesian. But those are details that we're going to get later. Just from an information point of view, I want you to realize, oh, there's enough information by making those projections, so-called projection, and the data that we collect is actually kind of along radial lines through the acquisition scheme that I described before. As it turns out, MRI is way more flexible than that. And in fact, from a mathematical point of view, you can actually show that when you apply a gradient in the presence, so after you excite, you apply a gradient, what happens really is that you're sampling the multidimensional Fourier transform of the image along certain trajectories. So depending on how you apply those gradients, if the gradients is constant, then you would collect kind of a line in a radial direction. But if you vary the gradients while collecting the data in a certain way, it's possible to collect data along spiral trajectories or along even Cartesian trajectories. And in Cartesian case, the nice thing about it is once you collect all the data, so you have to perform a few experiments like excite, apply a gradient, collect the data, excite, apply another gradient, collect the data, excite, apply another gradient, collect the data, and so on and so forth. So you have to repeat those experiments. But once you collect data along a two-dimensional Fourier transform, all you need to do is to do an inverse 2D Fourier transform in order to reconstruct the image. So it's very simple construction, extremely powerful. 99% of all clinical scans done today are done that way. The data is collected, sequentially. So every line is acquired after excitation, acquiring a line, excitation, acquire a line, and you can kind of see why MRI can become slow because data is collected then sequentially. And once you collect enough of K-space, then you'll be able to then reconstruct an image. All right. Okay, so that was acquisition, and hopefully you kind of see maybe or get some intuition of how Fourier plays into that role. Remember, applying a gradient maps the position of spins into a frequency that they emit. So obviously, if some Fourier analysis needs to be there in order to map from frequency back into an image or a position, right? So that is something that hopefully you're able to a little bit grasp. Maybe not the details themselves of how it's exactly being done, but at least conceptually why a Fourier transform is kind of needed. Now, another subtlety I want to talk about is a little bit about the excitation. So in order to excite those spins, so remember the spins are oriented along the main field direction. And in order for them to start processing and produces a signal, we need to perturb them somehow. And the way that we perturb them is we apply a radio frequency pulse. And if we have no gradient on and we apply a radio frequency pulse at the resonance frequency of the spins, at the frequency corresponding to, I guess it's the same frequency that they would have emitted if they would have been excited. So it's the same, what's called Larmor frequency. If we apply that radio frequency pulse, then that would then interact with those spins and will excite them. Okay, so with if I'm applying an RF and I have no gradient, then those spins everywhere in the volume would be then perturbed or excited. And once they're in the transverse plane or they have some transfer component, they start processing and producing a frequency. All right. So here's a quick question. What if I actually apply a gradient, and then while the gradient is on, apply an RF pulse? What would happen then? You know, actually, just from a little bit, maybe another intuition about those spins. If you think about it, let's say those spins were tuning forks, and all those tuning forks are exactly the same forks, and I apply a tone which is really the same tone that those tuning forks are producing. What would happen if I apply that tone, and it's going to be, let's say, very, very strong? What would happen to those tuning forks if I apply that?
I mean, they should start to become the new tone.
Yeah, they'll start vibrating, right? They'll start vibrating. If you apply like a tone at the right frequency, then they'll start vibrating. If you apply it at a completely different frequency, they won't vibrate because they won't couple to that tone, because it's really not something that they, that they correspond to their natural frequency. So a similar thing would happen for spins. So what would happen if I apply a gradient, a small gradient, to space, and then apply a radio frequency pulse? What would happen to that resonance frequency of those spins if I apply a gradient?
Wouldn't they change? So it'd be like the tuning, having a bunch of different tuning forks, and then when you apply the pulse, only one of them will go off.
Okay, well, it depends. Like everything in MR, it depends. You're right. What would happen is that when I apply a gradient, now effectively is I'm kind of creating a piano, or like, basically it's these become tuning forks, but slightly different. This would be higher frequency, this is the same frequency, and this is lower frequency, right? And if the gradient is small, that means that, the entire range here is going to be small, right? If I apply a large gradient, the frequency range will be large. If I apply a small gradient, the frequency range will be small. And so now if I apply a tone at this frequency corresponding to, some frequency of that, of this piano, then what would happen is that, those in center would couple strongly and would be significantly excited, whereas those at the edge are not on resonance anymore and would not couple to that radio frequency or will not be excited. Does that make sense? And so now we have something like what's called selective excitation, because we only excited really this portion of the spins, but we didn't excite those spins and those spins over here. Okay. Now, if I then wait, keep the gradient on, and then listen to those spins, then only those spins over here are going to produce this music, whereas those spins over here that were not excited are going to produce nothing. Does that make sense? So if you think about this now, in this case, it's not that the spins are producing music, but this is kind of like the tone that I'm using in order to perturb those tuning forks. And once those tuning forks have been perturbed, they keep emitting, those frequencies. Okay. But those that did not don't produce anything. Now, what would happen if I apply a stronger gradient? How does the picture change? If the gradient was stronger, how would this picture change?
Would that mean that fewer of them couple?
Well, okay, no. So
Like
I
if
have a
the
picture here, right
range-
at the bottom. I have a piano with like 3 keys, and I have spins on top. How would this picture change if I apply a strong gradient? What would be the range of frequencies then if I apply a strong gradient? Is it going to reduce or increase or stay the same?
Wait, can you repeat that?
Okay, so when I apply a gradient, that means that this spin over here will resonate at a slightly higher frequency.
Yeah.
And this spin over here will resonate at a slightly lower frequency. What would happen if I apply a stronger gradient?
Your bandwidth increases.
Yeah, this spin over here would generate a much higher frequency. And this spins over here would generate a much lower frequency. So the analogy would be is kind of having more keys in the piano, kind of more squeezed in, right? So, you know, in the same space, in the same length, now this would produce a higher frequency, this would produce a lower frequency, right? But
This
the spins have not changed in space.
this might be a silly
It's like-
question, but like why is it a greater frequency and not like sort of a louder spin, like more torque to it or something?
Ah, that's a good point. Okay, so I guess the magnetization really depends on the number of spins that you have, and it depends on the main field, which is 3 Tesla, for example. The field that we're applying with a gradient is not enough. Like, it's much smaller than a Tesla. It's usually 4 Gauss per 1 centimeter maximum or something like this. So it's not even getting to that rate, the high range. So it's really doesn't change the magnetization. It just changes the frequency, but it's not affecting the amount of magnetization being generated. So think about it as a small perturbation on top of a very strong one.
Okay.
Does that make sense?
Yeah.
So when I add when I create a big gradient or strong gradient, effectively the same space, the same length now would produce a wider bandwidth, like more frequencies. Okay. All right. So now I apply exactly the same pulse, which is this key. What would then it excite? Before it excited like a kind of a range of spins, but now it's going to be more selective. It's really just going to touch the spin that is that frequency, but the rest are just too far, so they're not going to be excited. So now you're selecting a narrower space, even though you're exactly the same bandwidth.
Does this also
Right, 'cause that-
correspond to like the bandwidth of the radio frequency pulse that you use?
So I use right. Okay, so absolutely. So that was kept constant before and to this slide. So before, again, the size of the key, remember, is just one key has a certain bandwidth, I guess. And then when I excite, that one key correspond to, I don't know, a few centimeters of space. But once the gradient is stronger, that one key corresponds to just maybe a millimeter. Does that make sense? And if I change the key, for example, to be that frequency, then I will excite that spin. So this is possible to then selectively excite spins by applying a gradient and then applying an RF pulse in the right frequency. And what if you want to select a larger band? What you could do, for example, is, play a wider bandwidth pulse. And for example, like pressing those 4 keys over here would produce maybe a wider bandwidth. But what is a wider bandwidth pulse in time? Anybody has an idea of what's a band limited pulse that you would apply?
You do a chirp.
Chirp is a good one, yeah. But typically we don't do a chirp. But yeah, actually, sometimes you do a chirp, sometimes not. Like everything in MR depends. Oh, sync. Who said sync?
I did. Sync. Yeah.
Who said sync?
Me, Daniel.
Good job, Daniel. That's another one. So chirp and sync are 2 band limited pulses that you can use. And by the way, often you'd see actually sync pulses being used over and over again in order to select slices that way. All right. So that's the idea of selective excitation. And therefore, there's certain interesting geometry. So if we excite a slice, then we only, the spins only would emit signal in 2 dimensions. And so we only need to encode the image in 2 dimensions. If we excite a volume, then the spins will emit signal in all 3 dimensions, and we'll need to encode all 3 dimensions. So the geometries in MRI are either exciting a whole volume, exciting a 3D slab, or exciting many, many 2D slices one after the other, and then encoding each one of them separately. So these are all, very typical things to do. And when people ask you kind of what is the slice, like, are MR images cross-sectional? And you can say yes, but not always, because sometimes it's 3D, sometimes it's 2D. Again, like everything at MR, it depends. And we'll get to that, hopefully, and you'll understand more about what slice selection actually means when we get there. Okay, so in order to produce an image, we had to excite spins. You all froze. Can you see me? Hello?
Yeah, we can see you.
Yeah.
And can you hear me? Because you suddenly kind of froze and became like still. And that freaks me out.
We can see you and hear you.
Well? Like,
Yeah.
how well? Like am I like really, really good?
Yeah,
Heard?
as always.
Okay. All right.
Yeah.
Okay. Thank you, Ekin. That's very kind of you. You see, that's a good TA. All right. So in order to remember to produce an image, what we had to do is, first of all, excite. So we can either do selective excitation or maybe non-selective excitation, but we need to excite the spins such that they start processing. The other thing that we have to do is encode an image, and the way we encode it is we applied a gradient, right? And maybe a gradient every time in a different direction. So effectively, we have to control the hardware and its timing in a certain way. And this is called a pulse sequence. Okay, so a pulse sequence diagram looks something like this, where you have a line over here of what the pulses look like. It's a timing diagram. And then you have here the hardware and MRI. So we have the RF, you have the gradients, and we have 3 gradients, one in the Z direction, which is a long domain magnetic field, one in the Y direction, pick your favorite axis, and X is orthogonal to all 3 of them. Okay, so GZ, GY, GX. And then we have our analog to digital converter when we're going to actually collect the signal, because we probably don't need to collect the signal all the time, only in times that are relevant for us to do. And the experiment would go like you would repeat n times a sequence such that you apply a radio frequency and then you do something to collect, and then another radio frequency and you do something to collect the data, and so on and so forth, and repeat that. Okay, and here in this case, while the radio frequency is on, the gradient in the Z direction was also on. You see that it's also on? That means that this is going to be slice selective somehow. Because if the RF is on while the gradient is on, that means that some of the spins are going to be excited, not all the spins are going to be excited. And then I'm going to apply some Y gradient and X gradient in order to encode the image, and then collect data during a certain amount of time. And then repeat that n times. Now, throughout here, the only thing that's actually changing in this case is the Y. And the way to actually represent this is as just a single diagram, which is repeated n times. And every time something is repeated, you show it as multiple lines in the same position. So here, everything, this is the same, repeated over and over again, exactly the same. The GX is repeated exactly the same. The only thing that is different that changes every time is the Y goes from high to low, and then high to, in this case, low to high, but not, that's just the detail. And this is what's called a pulse sequence diagram. And we're gonna plow through these, and at the end, you're gonna design your own, simulate it in MATLAB or Python, run it on a scanner. Like you'll do a lot with these type of things so that you really understand what those means. Okay, but this part over here is the selective excitation. You apply an RF in the presence of a gradient. And then this part is actually corresponding to the acquisition. So the spins start processing and producing signals over here. And here we're going to manipulate them somehow by applying the gradients and changing their frequencies while collecting the data, such that we'll be able to get some signal. And you can kind of see here that the X gradient is on while we collect the data. So if the X gradient is on while we collect the data, it's kind of like a projection. But we did this thing that we added before, that we applied different Y gradients. And so I'll talk about more of that later. But that's kind of like the idea of what's called a Paul sequence. And so the idea here with this type of a sequence is actually that things are collected along a Cartesian line. The way that it's done is immediately after excitation, your signal that is put out is actually the same as at the center of K-space. And then you're kind of traveling through the frequency domain of the object while spitting out that two-dimensional Fourier information. And once we get to this point, we're going to say, oh, now we're going to start recording. And as we move in the frequency domain and recording the data that we collect, that's what we store. And then the next time that we excite, we're going to collect a different line. And then the next time we excite, we're going to collect a different line, such that we eventually collect all the two-dimensional Fourier transform. So one line of K-space for each acquisition. We repeat n times to get an n by n image. Then we do a two-dimensional Fourier transform in order to do the reconstruction. So if the repetition for every line is about 400 milliseconds, let's say, a 256 by 256 image would be about 2 minutes to get collected. All right. Does that make sense approximately? Again, I'm hand waving a little bit. But I want you to understand that we have to repeat the experiment many times in order to collect. Now, one thing I have to say is that this time from here to here can be of an order of a second sometimes. The time from here to here can be about, I don't know, anywhere between 1 millisecond to maybe 20 or 30 milliseconds. And the time here to collect the data is often maybe 1 to 8 milliseconds or so, but not more than that. So this could be very long compared to a very short amount of time that you collect actually the data. Okay, that you have to understand. Now, once you understand that you collect data in the frequency domain, you can say, well, you know, how much of frequency domain do I need to collect? How densely I need to collect it? And as it turns out, if I collect only a small portion of the frequency domain, just in the center, this is the same as pretty much collecting a low resolution image, because I'm collecting only the low frequency information, so I'm going to get the blurred image. The more of K-space or the two-dimensional Fourier transform that I collect, the higher the resolution of the image will be. Okay, so the more I collect, then the higher resolution it will be. The other question is, how densely do I need to sample the K-space in the area that I collected? And that is actually determined by the Nyquist criteria, by the size of the object. If the object is large, so it has a certain field of view, then as long as the distance between 2 points in the frequency domain is smaller than 1 over the field of view. If it's smaller than 1 over the field of view, then I should be able to reconstruct this image with no problem. But if I skip measurements and I don't collect densely enough, what I will get is I will get folding or aliasing of the object. So I will get this type of an effect. And so in order to recover an image, I need to sample it sufficiently well and also sufficiently far in K-space. So these are kind of the two constraints. The more measurement I make, the longer the scan is. So you can kind of imagine that if the object is very, very large, it's going to cost me scan time. If I want higher resolution, it's going to cost me scan time. Any questions? No questions?
Yeah. Is there
Who
any
said yes?
limitations on I did, Daniel. Is that better?
Yeah.
Can you hear this? Is there any limitations on the
Yeah.
horizontal spacing?
Okay, so yeah, the spacing, all that stuff, really, I mean, it again depends. I mean, right now I'm showing you a Cartesian acquisition, but if it was spiral, then there was no really horizontal, right? If it was radial, then that's not, so it's really depends. Normally in one dimension, you say we're almost continuously sample. That's the direction of the gradient that you collect, that you apply the data. For example, this direction usually doesn't have a problem of sampling. Usually the repetition, the next repetition that I have to apply and collect a different line, that's the main issue in the distance. Usually the sampling is not a problem along one dimension. And along a spiral, it's not a problem along the spiral, but between spirals is a problem. In a radial trajectory, it's not a problem along a spoke, but it's a problem between spokes because you have to then repeat the experiment.
I see.
We'll get to that, but that's a really nice observation. Thank you for asking. Okay, so what's amazing about MRI? It's the contrast that it generates. I mean, I showed you the CT of the leg. I mean, it's bone or muscle, but that's it. And you can't really see structure inside the muscle. You could just see this muscle there. Maybe you see some structure in the bone, but that's because it's very high contrast. But really, it's impossible to see any, significant tissue contrast in CT. But MRI has this amazing and wonderful tissue contrast. I showed you, all the type of contrast you can get, both, the structural one, but also the functional one, diffusion, and, temperature and all that stuff, right? That's what's amazing about MRI. And so what I want to talk now very briefly is about two contrast mechanisms that relates to the relaxation of the magnetization that we leverage in order to produce these amazing, some of these amazing contrasts. So once magnetization is being excited, I said that it processes, right? But it has another dynamic. So beyond just processing, it starts going back to its original position, okay, somehow. So it will start, the transverse component will start decaying, and the longitudinal component will start rising, something like this, okay? Now, of course, it rotates also around itself, but I eliminated this by looking at what's called the rotating frame. So now it's all with respect to some rotation that happens, but this is just the relaxation component that I'm showing you, right? So it basically relaxes this way. So it relaxes fast, usually there is a transverse relaxation, which you can actually see here. So this is the projection onto the transverse plane, the black here. Can you see my my arrow? So complain that actually don't have a good arrow. So maybe I'll just pick up this spotlight. There you go. Can you see now? Can you see this arrow over here? This is the transverse orientation. And over here, this is the longitudinal one. So you can start seeing how the longitudinal component starts growing up, right? So transverse components decays, and then longitudinal component grows up. Remember that the signal that we collect is only proportional to the transverse component, has nothing to do with the longitudinal one. So it's only proportional to the transverse. So the way we generate contrast based on these is by playing with certain timings. And I want to give you a really nice analogy, which is the toilet analogy of how this dynamics actually works. Imagine a toilet. Can you imagine a toilet? If you can't, just look at this picture. This is a toilet that I took a picture of if you're having a hard time imagining it. A toilet consists of a bowl where you do your stuff in, but let's just ignore the stuff that you do, and let's just treat the toilet by itself by having water level inside. And let's say that water level corresponds to the amount of magnetization. All right. Beyond this bowl, this toilet has another important piece. What's the important piece? That the toilet doesn't work without.
Water tank?
The water tank, yeah. The water tank is the reservoir of magnetization that we're going to leverage. And then it has a handle. The handle is the RF excitation, okay? When we excite the spin starts processing, and now there's going to be water. The water is the transverse plane inside the ball. And that's the signal that we're going to then collect, all right? Now, the dynamic is very interesting. The dynamic is such that when I how do you call this, flush the toilet, the water level is, it's going to be a certain amount of water level, and then it's going to start draining. The rate that it's going to drain, I don't know. It depends. If you go to some like cheap motel, usually it drains really, really slow. If you go to a really, houses in Berkeley, from the early 19th century, maybe 20th century, also not great. But if you go to a super duper, I don't know, maybe 5-star hotel with large, large drainage, you press, it sucks the thing out of like there's no tomorrow, right? So each toilet is very different. And so we can think of each toilet is also different type of tissues. Tissues that, take time to clear the bowl, and some that are draining very fast. Same time, you've got tanks. Some tanks fill very quickly, and some tanks take forever to fill, right? So it could be quite annoying. And so how quickly the water in the bowl disappears, we're going to call it a T2 parameter. And then how quickly the water in the tank fills back up, we'll call it a T1 parameter. Okay. So the observed signal is in the bowl. Different toilets correspond to kind of different tissues. But I'm going to prepare now to press on the button to excite. And then what would happen? Well, what would happen is, okay, so here I did I tried to synchronize those videos to two videos. Basically, exactly when I pressed on this, the water starts flowing in the bowl, right? And our magnetization went down here because it was excited, and then started relaxing in the transverse component as well as relaxing in the longitudinal component. Now, what happened was that after a certain amount of time, a yellow toilet would drain much faster than, I don't know which color is this? Cyan? Gray? What is this? Gray? Let's say gray.
Gray.
So the gray one actually was draining slower, right? Now the time that happens from here, excitation is very quick. And then I waited, I don't know, maybe 20 milliseconds or so. And now what I'm going to do is now I'm going to apply a gradient and collect data. All right, now I'm going to, at this point, after I waited a little bit, I'm going to apply a gradient and collect data. If I do that, what would happen is that the signal that comes from toilets that are gray is going to be higher than the signal that comes from toilets that are yellow. Because we're looking at only the transverse component, and so the yellow ones are going to be smaller. Now, what does correspond to? This is exactly what I have here. It's called the T2 weighted image. The tissue that is bright, the tissue that decays slower than tissue that is darker. That means that in this case, there's a tumor here. You see the tumor? The tumor has a lot of fluid in it. The fluid takes time to relax and produces signal for a longer amount of time than let's say white matter over here. So white matter will be dark, whereas the tumor or fluid would be brighter. And this is called a T2 weighted image that you excite, you wait a little bit, and now you image at the right point. Then you wait till everything relaxes again, excite, you wait exactly the same amount of time, collect more data, and then repeat and repeat and repeat. So that creates an image that looks like this. This emphasizes how fast the water bowl clears, right? Or how fast the transverse component decays. Now, I told you that it's impossible to observe directly the longitudinal component. So how can we emphasize the longitudinal relaxation if we can't observe it directly? We can only observe the transverse component. So for that, there's a trick. And the trick is to try to create a certain longitudinal component and then apply an excitation, move it into the transverse plane, and then image quickly such that it emphasizes. And here is how it works, okay? The way it works is what we're gonna do is we're gonna continuously excite over and over again without waiting for things to relax. And so things are gonna look like this. When I do that, when I excite over and over and over again, you know, there's some water would clear up from the ball, but not all of it. But some water would also fill into the tank, but it's not going to be full. So there's going to be a certain steady state created that depends on how fast the water clears from the ball, but also how fast it fills into the tank. If the tank fills up very slowly, I'm going to have a very small level of water. If the tank fills up very quickly, I'm going to have much higher level of water. Does that make sense? So in the same way, I excite it and then wait. And then before everything relaxes completely, I excite again. And then I keep on going and create a steady state. And so after this point, after I waited till it relaxed a certain amount, now I excited it, and now I have some contrast that was created between the gray and the yellow, but it's mostly dependent on the longitudinal relaxation as opposed to the transverse relaxation, right? Because by the time I excited, and then I'm going to do it again, by the time I excite again, you know, all the transverse component also died completely. But it's only the longitudinal component that has a difference. And so now all this has been transferred into the transverse plane, and now the yellow tissue is going to have a higher signal than the gray tissue. And this is an image that's called the T1 weighted. Whatever is dark represents toilets or tissues that take time to recover their magnetization. They relax slowly back into the longitudinal position. Whereas if something is bright, that means that it recovered very fast. What is the brightest thing over here in the image?
The bone.
It's not bone. Bone we can't see really with MRI. You
Is it
see the
fat?
black stuff between here and this. This is the bone is the black stuff,
The
but
skin,
we can't really see bone very well.
the
It's the
dermal.
subcutaneous fat.
Yeah.
The subcutaneous fat is the brightest thing because fat has actually a very short T1 parameter. So it relaxes very fast. So it's brightest. And then House prefers T2.
You get a cervical, thoracic, and lumbar T2 weighted fast spin echo MRIs.
Okay. So yeah, T2 weighted fast spin echo MRI. By the time this class is over, you know what I'm talking about. That maybe now you know what T2 weighted, but fast spin echo, you will get to that. You'll also know what fast spin echo means. All right. So you'll be able to watch House and go like, oh wow. I don't know if you watch House. Anybody watch?
Yeah.
It's a good show. It's pretty bumpy.
So the is the weighting process done by like in an experimental way, like you would excite until you find this steady state, or can you find the weighting without like exciting a subject's tissue over and over again every time you do an MRI?
Yeah, so the tissue, the values of T1 and T2 for different tissues don't change significantly between subjects. They do change a little bit from subject to subject and from scanner to scanner because of the field changes, but they're not significantly. So you could target the timing such that you can emphasize this pretty well. And in more sophisticated sequences, they'll do some calibration to estimate the range, and then they'll optimize it better. But typically, you don't need to do that. You can say approximately T1 of gray matter is, I don't know, 850 millisecond, and T2 of gray matter is 150 millisecond, or something like that. And then, and so on and so forth. So based on this, you can then design something that would emphasize the differences between tissues. In fact, you can. What was the question?
So if when you're measuring when the atoms process, are they ever influenced by the neighboring atoms? Like, is there a pull from other atoms?
This is not atom that process. You have to remember that it's nuclei that process. The atom is the nuclei of an atom, and the question is whether there is coupling between between two spins. The short answer is yes. The long answer, it depends. That's pretty short too. In many cases that we do for imaging, it doesn't. And actually, some of those interaction actually leads to this relaxation, the decay. T2 decay is actually a lot with some interaction between spins, nearby spins, some of it. So, but that causes often loss of signal for some reason. But sometimes you'd get some coupling on certain molecules. For example, certain fatty acids. You might get some coupling between hydrogen on, the OH part with the, I don't know, with maybe just the H, and then they'll couple with each other. But that's beyond the class. But in spectroscopy, they use that a lot in order to infer molecular structure.
So it doesn't affect.
Does that make sense?
Yeah, so it doesn't affect.
Yes, it doesn't. That's not what I said. I said that it's more complicated. We can model this effect, and one way to model it is relaxation, that the signal decays. The other one is through this coupling, but that's beyond class, and you'll see that often we don't observe that in vivo. Or even if we do observe this, often we ignore it, and then we get artifacts. But it's a small effect. Okay, just a little bit about scanners at Berkeley. We have quite a few of them. We have 1 Tesla wrist scanner at Corey Hall, 70 Broker animal scanner at Li Ka-shing, 2 3T scanners at Li Ka-shing, and another 70 head scanner. UCSF has pretty much an infinite number of clinical and research scanner. Compared to, they have more scanner than a lot of countries in the world in terms of their amount of scanners that they have. I think it's around 40 or 50 or something like this. That's ridiculous amount of scanners at UCSF. So definitely there's a lot of access to scanners. And I know the Bay Area has hundreds and hundreds of scanners everywhere. In terms of access to research, definitely UCSF and Berkeley is a good place to be. And I'm not even showing you the NMR scanners that are on campus. There's also NMR facility as well. Okay. So as usual, I took more time than I planned, but that's okay. Because I know that that's going to happen, so it's planned. More time than planned. I don't know if you get my grip. but I don't. What I want to do now is to basically start now and go over the kind of prerequisite material. Uh-oh. Uh-oh. You know, and sometimes things work and sometimes they don't. Do you know that? Anita, how do you call these particles?
Cytons.
Cytons are these particles that eyes emit, right? Whenever people looking at an experiment or a demo. And these particles tend to interfere with the demo. And the more eyes you have looking at the demo, the more particles they are, so the more chances of that demo not working. Right? Did I explain it well, Anita?
Yep. Imaginary particles emitted from eyes.
It's not imaginary, I think they're real, you know? All right, but anything technical I can overcome. So let me figure out here. Yeah. Share screen. Can you see it? You want to see something amazing? Huh? It's something amazing. All right. So now I'm even able to write. Oh, this is a little bit of an update. So yeah, that's the new radio like X-ray. Pretty cool, huh? Lots of contrast between metal and bone. I wonder how the MR will gonna look like, and so soon we'll be able to see that, and I'll send you some. I'll show you some pictures maybe next time. Okay.
That's what they had to do to your leg?
What?
Is that what they had to do to your leg?
This? Yeah.
Yeah. Wow. I'm sorry. How are you feeling?
Well, I mean, it's a complicated question. It depends. What do you mean? I mean, now I feel great. I teach MRI. You know, it's like I'm at the, you know, it's like the height. This is the height of my career. But at the same time, I'm on the couch with my leg up, and most of the day.
Well, I hope the leg feels even
But the
better.
beauty, yeah, but the beauty about this is, first of all, titanium has very little susceptibility difference between tissue compared to, let's say, stainless steel. So I'm hopeful that I'll be able to get a good MR image without these metals distorting the magnetic field. And so we'll see what happens. I hope it's a good alloy. All right. But thanks, I appreciate the concern. Let's see. Okay, so I want to talk, basically it's a prerequisite material. I'm just gonna go and give you some overview of things that most of you know, some of you not, you know, don't have it embedded in their, you know, DNA. And really, by the end of this class, you really need to know this, right? Like you need to know what I'm talking about. You need to live it. You need to breathe it. You need to see it. You need to image it. And then you'd be able to understand really how this magnificent imaging modality produces images, but also how to debug all the issues that come up with MRI through this type of theory. So obviously, in order to do certain analysis, we often define a few functions. The function that we're going to use quite often is a rect function, or sometimes described this way. And the function is pretty much constant, 1 between minus 0.5 and 0.5, and a 0 elsewhere. Okay, this is how it's defined. And so it's a very useful function, for example, to crop, let's say, k-space, to crop an image, to crop something. If you multiply this function, then it will do that. Okay, so very useful function. Another function is the triangle, and the triangle is defined as 1 minus magnitude of x, as long as x is less than or equal to 1. So that is a triangle from -1 all the way to 1 with a maximum amplitude of 1. Okay, the triangle function. Another useful function is the step function, which is positive for x greater or equal to 0, and then 0 elsewhere. And that is useful for representing causal signals. If you multiply by this function, then everything is causal, right? It's like non-negative in time. But can also be useful, I mean, what's causal in an image, for example? I mean, but sometimes we would like to crop, let's say, half of the k-space or half of the Fourier transform for some reason, and multiplying by this function is very useful. Oh my God, this is one of my favorite. You should tattoo one of these on your favorite body part. I mean, this is a great function. First of all, nice looking one. Look at how wiggly it is, with a nice bulb in the middle and like really nice. You know, it's just beautiful function. With equal space, equally spaced zero crossing is just gorgeous. So it has zero crossing at 1, 2, 3, -1, all the integers zero crosses, and it has a really nice 1 at 0. And it's defined as sine of pi x over pi x. Sometimes people define sinc otherwise, like they define maybe without the pi. We're going to use the pi multiplied by pi. Okay. If you multiply by pi, then the zero crossings are on the integers. Okay. Does that make sense? It's a beautiful function. It's really my favorite function. Sinc. Oh, I mean, it should have a better name than the sinc. But you know, it's a convention. Maybe gorgeous function or something like that. I would argue something that's admirable, but the sinc, it's, you know, it's demeaning to this wonderful function. Now, another function that's important is the delta function or the impulse function. In the discrete case, it's very simple. It's 1 at 0 and then 0 elsewhere. But in continuous time, as we're going to be using it a lot, it's a weird beast. First of all, it cannot be defined by itself. It's defined through an integral. It's a function that's defined through an integral. So if I want to define what a delta function is I multiply this delta function by another function and then integrate from -infinity to infinity. And the result will be valuation of the other function at 0. Okay, this is how it's defined. It's a weird beast. You know, this function is 0 almost everywhere, except at 0, where it's an infinite. Where is it infinite? That's crazy stuff. Mathematicians invented it, and you know, but it's a beautiful invention. And the way that you write it is you write it as an arrow with amplitude 1. Okay, that's the delta function. It has beautiful properties. The first property is that it's 0 almost everywhere, except at 0, it will go to infinity. So that's a weird thing, but it really has another interesting property, which is if you integrate this function from -infinity to infinity, it's going to have an area of 1. How crazy is that? So it has finite area. It doesn't live anywhere except 0, where it's infinite. I mean, isn't that a weird beast? But it's an amazing tool. It's an amazing tool because of this property. And this property, what is this property really? Is you take some function, you multiply by this delta, you integrate, and that evaluates this function at 0. So it's a really interesting way to represent sampling. because if I multiply f of x by delta of x, it's the same as sampling f at 0. Okay, so this is how we're going to model sampling, by multiplying by these delta functions. Okay, and then integrate. This is how we're going to use that as a tool. Now, another weird thing about the delta function is if you scale the delta function, I mean, obviously, probably something shouldn't happen because you scale something, you know, but it's like 0 everywhere, except it's at 0, and there it's infinite. So how scaling going to even change it? But actually, when you scale it, it loses amplitude. How weird is that? If you scale the delta function by a, that means that you stretch it. It will lose amplitude by 1 over amplitude of a. So how much you stretch it. So you have to realize that part. Now there's different ways to derive it. For example, there's several realizations of a delta function. One realization is representing as a direct function, where this is delta x, right? And let me just remember. Do I have actually? I think I have a slide on this. Hold on. Okay, let me get to that in a second. The other thing is that if you multiply a function by a shifted impulse, so that would correspond to, so f of x multiplied by delta x minus x0 would be the evaluation of f at x0 multiplied by an impulse function. Okay, so it's kind of like an evaluation, except that it's still an impulse function. And of course, if I integrate over this, that would then correspond to f of x0. Okay, because the area of the delta function is 1. Okay, so multiplying the delta function by some, or a shifted delta by x, will then evaluate that function at x0. And then if we integrate, we'll actually get the value. All right. So the idea here is if I have some function that I multiply by a shifted impulse, then the result would be pretty much an impulse with the height of the impulse being the same height of the function at that point. All right. Now, just quickly over here, there's many realization to these deltas, but one realization is to think of the delta function as being a rect that is 1 over delta x, rect of x over delta x. Basically, it's a rect with area 1 that that has a width of delta x and a length of 1 over delta x. So it has an area 1. And then if we take delta x to 0, that means that the width of it is going to go to 0, but the height is going to go to infinity. So that kind of sounds, but the area is always going to be 1. So that's a kind of a realization of a delta function using kind of a rect. And from that, it's very easy to derive how the scaling property correspond to 1 over that. Okay. If you wanna be more clear on this, just take a look at the slides again and see how it's being derived. I don't want to spend too much time on it. Okay, another useful function. So if we're definitely talking about one delta function, then a train of them is even better. Pick your favorite train service: BART, Amtrak, Shinkansen. I don't know what's your favorite train service. It's a delta train or an impulse train, and the way that it's written is as this is called a shin. It's a letter both in Hebrew and in Cyrillic, also called Shah, I think, in Cyrillic, shin in Hebrew. And the reason that it's used for this function is because it has this train of impulses. So it's an impulse train. And the way that this function is defined is that the sum of that goes of n goes from minus infinity to infinity. So it's an infinite train of shifted impulses at the integers. So every integer you'll have an impulse, and that impulse amplitude is 1. Okay, so an impulse train that every integer will have an impulse, and the impulse amplitude is 1. The Shah function. We're going to use this quite a bit in our derivation. The question is, so this is actually very similar to a sampling operation at, let's say, t equal 1, t equal 2, t equal 3, and so on and so forth. So at the integers. But sometimes we want to change our sampling rate. And the question is, how can we represent an impulse train with spacing that are delta x as opposed to being spacings of 1? And the way to do it is to go, again, to do this impulse train that goes from minus infinity to infinity, but just shifted by delta x times n as opposed to just n. Okay, so the question is how this corresponds to this. How do I write that as a function of this Shah function? So what I want to go is I want to reach this type of a form such that I can represent this in some scaling and stretching of this function. So what I'm going to do now is I have a delta x times n, and here it doesn't. Here it has x times x minus n, right? So I need to make it look something like that. So what I'm going to do is I'm going to take the delta x out. So delta x multiplied by x over delta x minus n. And if I do that, what is this? Well, here's a scaling of a new variable that's shifted by n, right? So if you remember, delta of a times x is 1 over a delta of x. Therefore, the whole thing over here is the same as 1 over delta x. The sum goes from minus infinity to infinity of delta x over delta x minus n. And so the nice thing about it is that now this is actually a Shah function that is scaled by delta x. And here it's another scaling. So if I have 1 over delta x, Shah x delta x, that gives me an impulse train with amplitude 1 that is spaced by delta x. Okay, so that scaling over here is a compensation such that the delta functions actually have amplitude 1. And that comes from this derivation. Okay, so you have to remember that every time that you want to create sampling with, let's say, 2 delta x or something like this, you have to scale this at the Shah function as well in amplitude such that they will have 1 at the deltas. All right. So extremely useful to model sampling. Multiplying by this function is very nicely representing sampling at intervals of the delta x, right? Because it's the same as multiplying by this. So it's evaluating the other function at spacings of delta x. All right, let's talk about systems. What is a system? Well, a system is something that you take some signal, you push it through that system, and something else comes out. Okay? And those systems often have various properties, but the type of properties that we're going to look at, one of them is going to be linear. And in order for the system to be linear, it should satisfy certain properties. It should satisfy a superposition. What does that mean, superposition? Well, if I take g of x, I push it through the system T, and I get y of x. Now, what happens if I have now 2 signals that are added together first and then pushed through the system? As it turns out, if the system is linear, what I do is actually take the individual signal, I can take G1, push it through the system and get Y1, push G2 through the system and get Y2, and add them together, and that would be exactly the same as first adding the inputs and then pushing through the system. It's extremely useful property. It's not a trivial property, but it's extremely useful nevertheless. The other one is the scaling. So the scaling property tells you that if I scale the signal, it's the same. If I scale the input, then the result will be a scaled output. Now, is that true every time? What if I have a signal, let's say t equals x squared? Is scaling preserved?
Nope.
No, scaling is not preserved, right? What about superposition? Also no. So obviously there are systems that are nonlinear, but if I have those two properties, both the superposition and scaling, then I can call the system linear. What about the system t equals 1 plus x? Is that a linear system?
Yes.
Who says yes? Raise your digital hand. Only one person raised their digital hand. 2 people raise your digital. Who says no? Raise your digital hand with like a stop or something like that. Who says no? Those that says no, they're right. This is not a linear system. It doesn't satisfy superposition. It doesn't satisfy scaling. This is an affine system. Okay, because of this bloody one, you know, it's non-linear. The fact that you add some constant to something, you know, it makes it non-linear. It's an affine. Okay, you have to, that was a tricky question. Another property, very useful one, is shift invariance. And shift invariance says the following. If my input is shifted, that's going to shift my output by the same amount. Okay? If I shift my input, the output is shifted by the same amount. Extremely useful property. That means that the system behaves the same no matter when the input is being, you know, put in, which is extremely useful. All right. There's a lot of for example, non-shift invariant systems. Can you give me one? Is that shift invariant? Is this linear, by the way? Is this system linear? You see, what I expect from you is I wake you up in the middle of the night, you know that this is linear. You take a signal, you multiply by some cosine, you know, 2 pi f0x, you know, if I scale this, if I scale gx by a, you know, the whole thing will scale. If I also have you know, g1 and g2, you know, it will still, that's no problem. So it satisfies superposition and scaling, no problem. So this is a linear system. Is this a shift invariant? That's the other question.
No.
Why is it not?
Mm.
You're right that it's not.
Yeah.
And the reason is
wait.
because the input only shifts this, so it'll be multiplied by slightly different ways. This is not shifted, right? Because it's not an input.
Yes. Yeah.
That's the input. So this is a non-shift invariant system. But this is a modulation. This is like radio, all that stuff. This, multiplying by cosine. It's linear, but it's not shift invariant. You have to remember that, right? That's like that's a prelim question. That's a EE120 question, EE123 question. Many questions. Definitely 225E. So good stuff. Now, so if you have actually a class of systems that are linear and shift invariant, they have very interesting useful properties. And one of them is the convolution property. So the convolution between two signals is defined by, usually it's written by a star, but it's the integral from minus infinity of gx minus tau times h of tau d tau. Who's not familiar with convolutions? I'm not going to teach convolutions, but you really need to kind of catch up on what convolution is. If you're not familiar, then please look at the convolutions in a material in E120 or discrete convolution 123. It's crucial that you understand convolutions. Now, in the case of linear shift invariant system, why this is useful, this operation? It is useful because if I have an LSI, linear invariant system, and I input an impulse into the system and I measure the impulse response. So I put an impulse into the system and I measure its impulse response. Okay. Here's an example. Oh, I ran out of time. You know what? Let me just show you this and then I'll finish. Do you know this app called Sensors? It's a pretty cool app. So this app shows the accelerometer of my iPad. Okay. Can you see? All right, I'm gonna try to show you what is the impulse response of the system. Ready? Look at my video. Can you see the iPad? Or
Barely.
Barely, huh? Let's see if I can do something about it.
Turn off your background picture.
That's what I'm doing.
Yeah, okay, thanks.
See the iPad? Do you see the screen? You see the impulse response? Man, that hurts. I shouldn't have done that. It's the wrong leg. All right, I'll be more gentle, right? Yeah, you see the impulse response? Okay. So this is the impulse response. Now, who cares about this impulse response? Well, as it turns out, if you have an LSI system, you care because the impulse response tells you everything that you want to know about the system. It tells you so much that once you have an LSI system and you know the impulse response, given a new input, g of x, I don't need to even know to measure the output. I know that the output is going to be g of x convolved with h of x, which is the impulse response. So I know everything that I wanted to know about the system from its impulse response. So the impulse response are the DNA of LSI systems. So it's completely useful. Now, so it's described through this convolution. So the convolution of the input with the impulse response will then give me the response of arbitrary inputs. That means that if my iPad was an LSI system and I measure the impulse response, now if I, I shake it an arbitrary way, I can predict what the output is going to be. Or even more important, if I want a desired output, maybe I can actually create an interesting input, knowing how the output is going to be based on the impulse response, such that I'm going to design the output maybe that I want, or at least as close as possible to what I want. All right. So one thing about convolutions is often leads to a blur, not always a blur, sometimes it's enhancement, but often it's a blur. And for example, a convolution between two rects would then result in a triangle function. And you can go through that and do this exercise if you're interested in. All right. So next time I'm going to talk to Ekin about tomorrow. Maybe we'll do a review, continue this review, because I don't want to spend too much time on this, and I'd rather actually talk about MRI as opposed to that, because then I want to get to interesting topics as we go. So we might leverage the discussion tomorrow for more of that. But if not, then we'll continue on Thursday. So we'll do a discussion among the stuff. You can also tell me what you prefer, but everything will be recorded in any way. So I don't see that as a huge issue. All right.
Can you post these notes?
Anyway, what?
Can you post the notes, these?
Yes, we absolutely, all the notes, from the previous ones have been posted, and I'm going to post these too.
Okay.
Yeah, all the notes are going to be posted. I'll try to do it beforehand. I have to tell you that I'm a little bit behind, so that's why I haven't posted them. But what I'm going to do is I'm going to have actually a long set of notes, and they're going to be used for several lectures, and they're based on topics and based on chapters. So this is chapter 2 in the book. Then we're going to have a few lectures on chapter 3, but they're just going to be one set of notes. So I'm going to post all of them. All right. So I'll see you all either tomorrow or on Thursday, and we continue with this material. And the next topic that we're going to cover is chapter 3, which is, I'm going to look at my book, my new book. Overview. Classical description of MRI. Smells so good. Smells like polarization. All right. Have a nice day. And and stay dry during the storm tonight. And if you can, tomorrow try to go somewhere that you can maybe either see Mount Diablo or Mount Hamilton. There's going to be snow probably. So there's going to be snowy peaks in the Bay Area. So it's not the typical view. Highly recommended. Bye, everyone.